In our last class, we have seen these things. Just I will explain, and I will proceed to the third unit. Okay, binomial array. We are giving the non-uniform amplitudes to the antenna elements. Okay, the amplitudes are arranged in such a way that the radiation pattern has no minor lobes. Okay, um, yeah, in our last class, we have seen some examples. Suppose we are having 4-point sources. Okay, the distance of separation between each source is lambda by 2. Okay, we know the resultant electromagnetic intensity at the observation point is given by E is equal to cos pi by 2 phi, right? Okay, this pi is actually general. This equation is cos BD cos phi by 2. Okay, B into D, beta D cos pi by 2. Okay, if you substitute beta is equal to 2 pi by lambda and D is equal to lambda by 2, we are getting this expression for this type of array. Okay, in our last class we have seen. Okay, if the distance of separation between each successive antenna elements is lambda by 2, then the resultant electric field intensity is we are getting in this way. Okay, similarly the resultant radiation pattern is nothing but, okay, this is a simple broadside array case. Okay, the resultant radiation pattern is the individual pattern multiplied by the group pattern. The group pattern means this is one group, this is another group. The distance of separation between these two groups is lambda. Therefore, the group pattern is like this, and the individual pattern. Individual pattern means 1 and 2 is one group, 3 and 4 is another group. This individual radiation pattern is like this. Why? Because the distance of separation between these two antenna elements is lambda by 2. Therefore, the radiation pattern, okay, here I have taken the broadside array as an example. That's why I have written like this. Okay, now the individual radiation pattern x or y is like this. The group pattern of x and y is this. Now the resultant is, to multiply these two, we are getting this is the resultant radiation pattern. In this radiation pattern, we are having side lobes are there. Okay, unnecessary we are wasting the power in side lobes. Okay, if you can able to arrange these antenna elements in such a way that otherwise in a binomial form or binomial array, we can able to eliminate the entire side lobes. How we can do this thing? Simply arranging these two antenna elements in such a way that the distance of separation between the group elements is lambda by 2. Okay, the group elements, here 1 and 2 is a one group, that is x group. Okay, if I am taking this as a point source, middle point is the this is the point source for this group x, and 3 and 4 is another group. The middle point for this group is this is y. See here, this is the y here. Now the distance of separation between these two center points, this is lambda by 2 only. Okay, therefore, okay, the group pattern also, the distance of separation between the point sources in group pattern also lambda by 2. Therefore, the group pattern is similar to the individual pattern. If you multiply these two, the resultant pattern also coming like this. Okay, okay. If you want to write the resultant electric field intensity formula for this type of array, okay, we are getting E is equal to cos square pi by 2 cos square. Please try to evaluate this equation. We already know how to evaluate the equation for this type of array. Okay, now the array is like this. Okay, please try to solve the equation and find out whether this equation is correct or not. Okay, please substitute the phase difference and that equation and try to evaluate and find out the electric field intensity. Okay, this is the, in this case we are having the resultant array, binomial array. Here this is I, this is 2i and this is I. Therefore, we are getting this equal to cos square pi by 2 cos square. Okay, this is the pattern we get. Okay, if you take the 8-point source case also, okay, in this case also, here we are arranged these two group of arrays. Okay, this is 4 and this is 4. Okay, in such a way that the group of the resultant the groups, the distance of separation between these two groups. Let us, this is X and this is Y. The middle point is coming here. For this also the middle point is here. Okay, now the distance of separation between these two group elements is lambda by 2. Therefore, the individual radiation pattern and group pattern also same. Okay, if you write this one, we are getting this type of distribution. Okay, here the magnitude is distributed like this. This is I, 3 times of I, 3 times of I, and I. Okay, for this, if we calculate the resultant electric field intensity, we are getting this type of formula. Okay, please try to solve this also. Okay, if you can able, if you're not able to find out, please let me know. I will help you. Okay, this is the resultant electric field in this type of binomial array. This is equal to cos cube pi by 2 cos phi. Okay, here also the unit pattern of x or y is a uh, the radiation pattern is similar to the group pattern. See here, this is the radiation pattern of x or y. What is this x? X, here this is the x. Okay, earlier problem we have solved the radiation pattern of this x or y element. What is that element? Here this is the radiation pattern. Similarly, the group radiation pattern of x and y. Okay, here also the distance of separation between these two elements is lambda by 2. Therefore, the resultant radiation pattern is multiplying the individual radiation pattern and group pattern. Getting this is the resultant radiation pattern. Okay, in this way we can able to eliminate the side lobes. Okay, we are eliminating the side lobe means we are reducing the amount of energy wastage. Okay, in that way we can able to efficiently radiate the electromagnetic energy in a required direction. Okay, in general case, if the binomial array is having n elements, okay, the resultant electric field intensity, that equation is E is equal to cos power n pi by 2 cos phi. Okay, okay, here the n is equal to these values we can able to find out by using the Pascal's triangle. Okay, this is the magnitude of current distribution in a binomial array. Okay, if in a binomial array, suppose we are having one element, we are giving the current I. If we are n is equal to 2 also, we are giving I and I. If it is having 3 elements, okay, for first element we will give the current I, second element we are giving the current 2I, and third element we are giving the current I. Okay, in this manner, okay, if we give the magnitudes to the antenna elements, we can able to eliminate the minor lobes or side lobes. Okay, at the last class you have seen this Pascal's triangle also. Here you have to remember these 3 formulas here. One is length of the binomial array. This is the equation. And the other one is, this is the half power beamwidth and this is the directivity. Okay, this about the antenna arrays. Okay, in antenna arrays we have studied broadside array, end fire array, and pattern multiplication, and also enhanced directivity using Hansen Woodyard end fire array. And lastly, we have studied this binomial array. Okay, the main difference between broadside array and end fire array in this comparing to binomial array. In binomial array, we are eliminating the minor lobes by providing non-uniform magnitudes to the each antenna element. That thing you have to remember. Okay, now we want to start our third unit. In just yesterday, I have given the brief introduction to the third unit. Here, the third unit is mainly discussing. We will discuss about UHF, VHF antennas and microwave antennas. Okay, based on the frequency, range of frequency, we can able to classify these antennas. Okay, see, suppose if the antenna, the range of frequency, the operating frequency of these antennas, if it falls in the range 30 to 300 megahertz, that type of antennas is called very high frequency antennas. Similarly, if the operating frequency of an antenna in the range 300 to 300 megahertz to 3000 megahertz or 3 gigahertz, these type of antennas are known as ultra high frequency antennas. Okay, the best example for UHF and VHF antennas are Aggie-Wood antenna, folded dipole antenna, folded dipole. This is see here. Again, we are studying the dipole antenna. We'll study the dipole antenna, but it is a folded dipole. Here we will use two dipoles. They are arranged in a systematic way, such that it will form a folded dipole. Similarly, helical antennas. There are so many UHF and VHF antennas are there, but in our syllabus, we are mainly focusing our attention on Yagi-Uda antenna, folded dipole antenna, and helical antennas only. Okay, these VHF and UHF antennas are used in mobile communications, land mobile communications. Similarly, public communications, okay, industries, automobiles, vehicles, okay, aircrafts and ships. Communication purpose, we will use this VHF and UHF antennas. Okay, um, these are the three important UHF and VHF antenna. Yagi-Uda antenna, folded dipole antenna, helical antenna. You have to be familiar with this terminology. Okay, if you are listening this lecture first time, okay, this may be a little bit confusion, but once you understand these concepts, you will be understand. You can able to understand all these antennas and differences between them and their operation also. Okay, now uh, microwave antennas. Okay, if the operating frequency of these antennas they are more than 3 gigahertz, okay, 3 gigahertz frequency, they are the type of antennas are called microwave antennas. Okay, these microwave antennas are operated at microwave frequencies. Okay, microwave in the sense the wavelength of the waves are in micro meters, right? You can understand like that. Okay, similarly, the best example for this microwave antennas are parabolic reflector antennas. Okay, like they are like dish antennas. Okay, and horn antennas and lens antennas. Okay, in our syllabus we'll study this type of these three categories of antennas we'll study. Okay, we'll study one by one later. And the microwave antennas are mainly used in microwave communication, radar communication, and satellite communication, radio astronomy. Okay, electronic warfare like okay guided missiles. Okay, in that guided missiles also this type of antennas are mounted on this um, this that missiles. Okay, in that missiles they are able to track the target, and finally it will reach the target, and it will able to destroy the enemy aircrafts or enemy vehicles. Okay, in that purpose also this type of antennas are used. Okay, now um, in VHF and UHF category, we'll study the Yagi-Uda array antennas, or Yagi-Uda array or Yagi-Uda antenna. Okay, here we are saying that it is an Yagi-Uda array. Array means there are two or more elements are there. Okay, earlier last class I have mentioned Yagi and Uda. They are two different professors or scientists. Yagi uh, is a scientist. Okay, he translated the transcripts that are developed by this Uda scientist, a Japanese scientist. Initially, he developed this technology, and he written the papers in the Japanese language. Now, finally, the professor Yagi, he translated that Japanese scripts into English language, and he tried to design, and it can able to available to entire world from that day onwards. That's why this antenna is called Yagi and Uda array or Yagi-Uda antenna. Okay, this antenna is becoming available for our use from 1940s onwards. Okay, this Yagi-Uda antenna mainly consisting of three elements. One is the reflector. One reflector is there. One driving element is there, and one or more directors are there. We'll discuss what is this reflector, what is this driving element, and what is this directors one by one. Okay, first here the driving element, driven element. Here see driven element or driving element. You can say that is the element. It is like an antenna. Okay, we are giving the input signal to this driving element. Okay, see here what I am saying here. DE is the driving element is nothing but a half-wave dipole made up of a metallic rod. Okay, this driving element is nothing but a folded dipole. Okay, later we'll discuss in our next topic is folded dipole. Generally, this driving element, whatever we are mentioning here, this driving element is nothing but a folded dipole antenna. Okay, that we'll discuss later. All the three elements are placed parallel and close to each other. Okay, by in designing this Agibuda antenna, the three elements. What are the three elements? One reflector, one driving element, and one or more directors. They are placed parallel and close to each other. Okay, here we will study the first we will study the basics of Agibuda antenna, the structure of Agibuda antenna, the radiation of Agibuda antenna, and designing of Agibuda antenna. How to design this Agibuda antenna. We'll see the advantages, disadvantages, and applications. We'll discuss all these topics. These 7 topics are there. One by one, we'll go through. First we'll see the basics of Agibuda antenna. Okay, this Agibuda antenna is a directional antenna. What do you mean by directional antenna? A directional antenna is nothing but it is a the direction means, okay, it can able to receive the electromagnetic waves in a particular direction only. Okay, that's why we have to adjust the antenna so that we can able to get the good reception. Okay, that's why it is a directional antenna. Okay, it is it has the operating frequency above 10 megahertz. That's why we are calling it as a VHF and UHF ranges. Okay, we can use this antenna. Okay, it can be used for 40 to 80 kilometers distance. Okay, the range of this antenna is around 40 to 80 kilometers. Okay, in some cases it will more than it is up to 100 kilometers also. You can use this type of antennas. Um, in this antenna, this total 3 elements are there. These 3 elements are classified into 2 types. One is active element and other one is a passive element or parasitic element. Okay, active element means what? Active element is nothing but this is the driving element. Whatever the input signal we are giving to this active element. What is this parasitic element? Here we are having reflector and directors are parasitic elements. What is a parasitic element? The element in which the current is induced due to the field in other elements. These parasitic elements will carry the currents due to the field produced by this active element. Actually, we are giving the input to the active element. Because of the current passing through this element, it will induce the electric field, electromagnetic fields. Because of that, okay, there is a current that will be induced in this parasitic element, that is reflector and directors. Okay, don't worry about this thing. The driving element is the active element. Reflector and directors are the parasitic elements or passive elements. Okay, here see the parasitic element is not connected to the supply. We are not giving any input to this supply. We are giving the whatever the supply, whatever the input is, that the input is given to this active element only. Okay. Next, this is the basics of Agibuda antenna. Now, the structure of Agibuda antenna. How the Agibuda antenna is there? Okay, earlier we have seen that the 3 elements are placed parallelly and close to each other. Here, see, there is one supporting rod is there. Okay, to that rod, by using these clamps, we will arrange these antenna elements. What are the 3 main basic components of Agibuda antenna? One reflector, one driving element, and two or more director elements. See here how many are there. This is a reflector and this is a driving element. Okay, this is one director and this is another director. These are the parasitic elements. This whatever this I have written in blue, right? This blue color metallic rod. Okay, this is twisted. Okay, in this shape. This is the driving element. Okay, this driving element is nothing but a dipole antenna or a special kind of dipole. 2 dipoles are there. Okay, the 2 dipoles are arranged in this manner. That's why this is called as a folded dipole. You can say this element is called folded dipole antenna. Okay, and these are the directors. Okay, by using these directors, we can able to minimize the side lobes. Side lobes mean we can able to minimize the power in the side lobes. This is the stand. Okay. Uh, this is stand which is placed on the ground. Okay. The spacing between the driving element and directors are kept between 0.1 lambda to 0.15 lambda. Okay, that is the design constraints. Okay, now this is the structure of the Aggie-Wood antenna. Okay, now individually we'll see how the radiation pattern of this Aggie-Wood antenna uh, we can able to see. Suppose this Aggie-Wood antenna, suppose it is having only the driving element. Okay, let us say this driving element is the folded dipole. Okay, without having these reflectors and this directors. Suppose if you place this folded dipole and if you give the input signal to this folded dipole, okay, we will get the radiation pattern like this. Okay, see, this is the radiation pattern of Aggie-Wood antenna. But here we are using only the driving element. Driving element means this is the folded dipole antenna. If you provide the supply to this folded dipole antenna, okay, we are getting the radiation pattern like this. Actually, these two will join here. It will come to near. But drawing this, okay, this there is a separation. Okay, actually, the radiation pattern, okay, of this driving element, this is the folded dipole antenna. That's why we are getting like this. This is the shape. Suppose if you use suppose if you use this is the reflector element. This is the reflector element. Reflector element. If you place the reflector element, see here the back lobe and the back lobe power that will be reduced, and we are getting the two side lobes. Okay, we are getting the side lobe, and see we are getting the maximum directivity in this opposite direction. Okay, that's why it is called as a directional antenna. Okay, it is having the maximum radiation in this direction. Okay, minimum radiation in other directions. Okay, suppose if you place one or more directors here, see here, if you place uh, director elements, okay, if you place director elements, we can able to further increase the directivity of this main lobe, and here we can able to minimize the power in the minimize the power in the back lobes or minor lobes. Okay, see, this is the reflector element, this is the driving element, these are the director elements. If by using this number of director elements, we can able to minimize the minor lobe radiation. This is the minor lobe radiation. Okay, this is the radiation pattern of Aggie-Wood antenna. Now, the design constraints for this Aggie-Wood antenna, 3-element Aggie-Wood antenna, is what are the 3 elements? Reflector, driving element, and directors. Okay. Here, these are the things you have to remember. You have to by heart these things. The length of the active element, LA. Okay, the length of the active element should be 478 divided by the frequency, the operating frequency in megahertz. Okay, based on that, okay, you can able to design the length of the active element. The active element is the folded dipole antenna. Okay, based on our requirement, based on the frequency we are using, okay, based on that the length will be varied. Similarly, the length of the reflector element also is the right. This is the, see, this is the reflector element, this is the driving element. See, they are not uniform. See, in this may see here, this the length of the reflector is more compared to the driving element. Okay, compared to this director, the length of the driving element is more. Okay, see, it is forming like one triangle. Okay, this is the shape of the Aggie-Wood antenna. Okay, similarly, the length of the reflector element is like this. Okay, 492 divided by frequency and magnitude. Okay, our session will close in 10 minutes. Please try to rejoin. So similarly, the length of the directors, okay, the length of the directors should be 481.2 divided by frequency in the frequency in megahertz. The spacing between the elements should be 0.25 lambda. Okay, this may be varies from different types of different designs. Okay, but normally this should be 0.25 lambda. This is about the design constraints for this 3-element Aguda antenna. What are the 3 elements? Active element, the reflector element, and director elements. Okay, the lengths of these elements can be decided by using this formula, and we'll construct the 3-element Aguda antenna. Okay, the advantages of Aguda antenna is, okay, it is a high gain antenna. The gain is about 9 dB. Okay, it has high back to front to back ratio. Okay, back in the back sense. Okay, a back lobe, the we are by using the number of directors we can able to minimize the back lobe power, minor lobe power we can able to reduce. That's why we are getting the high front to back ratio. And this antenna, the construction of this antenna is very cheap. Okay, it requires very less amount of amount for designing, and it is also very lightweight. Okay, this is designed by using the aluminum foils. Okay, that's why the weight of this antenna is also very light. And some disadvantages also there. Okay, if you want to go, if you want to design this antenna for, okay, high gain, if you want to exceeding that gain up to 20 dB also we can able to extend this gain. But if you are going for 20 dB gain Aguda antenna, the length of these the elements, okay, the reflector element, the driving element, and direct elements, the length will become very long. That is the main disadvantage. Okay. Uh, Coming to the applications of Aguda antenna, okay, these antennas are designed, okay, in high frequency range and very high frequency range and ultra high frequency range also. Okay, see here, based on this frequency range, the length of the reflector, driving element, and directors may vary. That's all. Okay, different frequencies. Okay, we can able to design different Aguda antennas with all the elements. Okay, these antennas are popular for TV, home TV receivers. Okay, these Aguda antennas are in last take past 10 years. Okay, 10 years back, these Aguda antennas are very popular. You can able to see in every home. We have this Aguda type of antenna. Nowadays, we are not using this type of antennas, and it is used for point-to-point communication purpose also. Okay, for the intercommunication between two ships, or communication with the base stations. Okay, land mobile communications. In that purpose, point-to-point communication also, these type of antennas are very useful. It is having narrow bandwidth. Okay, it is land mobile applications, industrial applications, and astronomical and defense related applications also. These antennas are used. Okay, this Aguda antenna is this. Okay, we have left with only 6 minutes. Our next topic is folded dipole antenna. Tomorrow I will discuss this folded dipole antenna. Okay, this folded dipole antenna is nothing but the driving element of the Aguda antenna. Here the driving element is there, right? This driving element, it is a folded dipole antenna. Okay, our next topic is folded dipole antenna. I will discuss this topic in our next class. Now I am stopping here. Okay, tomorrow I will discuss this folded dipole antenna. If you have any questions, you can ask now.